Hey guys, okay, so I'm going to get straight on with this today. I'm going to be doing the May 2022 paper. So this is just a continuation of my series. I'm just setting up my video on screen so I can check that the sound's all working. It's going to blare out in a sec, guys. I apologize for this blast of sound if you get one. It says new management, like that. Okay, it just says waiting for me, which is interesting. I'm assuming it's going to come on in like 10 seconds or so. There. Amazing. Okay, cool. So I've paused my video there, but I can see the chat. Okay, May 2022 paper. I'm going to be doing this all the way through. I have not looked at the mark scheme. I do not expect to get 100%. I made one error in the January paper, but it's nice just for me to point out, I've picked up from that when you see those water crystallizations and it's asking you how to improve, it's wanting us to say, you heat until constant mass, and it gives us a better idea of how much water was in it. You're ensuring all the water is lost. That was the mark. Yeah, ensure all the water is lost from it. Okay, I'm going to share my screen and get rid of my camera. I've forgotten my camera again. Not that it really matters, because you don't need to see my face during it. Okay, I'm going to do share entire screen. And then I do that to get rid of my face, but I leave it there because it leaves the sound on. Cool. I've got someone on the chat already, which is amazing. Let me know if this is all working okay. Okay, so May 2022's paper. Take off my keyboard. Let's crack on with this, folks. Okay, so I'm going to fill this in red. Mr. Duncan, gotta love it. I didn't fill out my name on the last one, and I felt like I should have. Okay. Right. Question number 1. Elements in their most stable states exist as. Okay, that's actually a really interesting question to start off with. Atoms in giant structures only. Well, we know that silicon and carbon both exist in giant states, so that is true. But not only. We know that we need elements in their most stable states. Well, the elements we've got the diatomics who go around in molecules, and we've got noble gases who go around in atoms. So atoms in molecules and atoms in giant structures only. We're missing the noble gases. Isolated atoms, there's your noble gases, and atoms in giant structures only. Isolated atoms, atoms in molecules, and atoms. So the answer is going to be D. Now, there'll be students out there who will probably want to choose maybe giant structures only, thinking that, it's going to be the most stable. But actually, the most stable elements out there are the noble gases. So in reality, hi, who's that? Gamut? Thanks for coming, Gamut. Thanks for being here. Oh, is it Garnet? I can't read the name from here. Garnet, nice to see you. Thanks for coming along. Ask any questions in the chat if you've got any. The most stable elements are noble gases. So A and B are immediately out the window anyway. And then the difference between C and D, giant structures. But the thing is, not all elements exist as giant structures, so the only answer would be D. A sample of nitrogen gas contains 1.204 times 10 to the 22 molecules. That's less than a mole, folks. I know that you don't need to know this. It's actually in your data book. It's actually, I think, probably at the back of the paper, but it's useful to know Avogadro's number. It really is, because there are times when they'll ask you questions to calculate it. The calculation won't give you that exact number, but it'll be really close. Common things tend to be 6.015 times 10 to the 23. They don't want to give you 2 because they know that students would just know the answer immediately. But it's a useful number to know. What is the mass of the sample? So we've got nitrogen gas, and we need to work out how many moles there are. So we know that that's a smaller number than Avogadro's constant. So what I'll do is I'll do 1.204 times 10 to the 22 divided by 6.02 times 10 to the 23. That's going to give me a 0 value. It's going to be 0 point something, and that's going to be the number of moles. So 1.204 exponential 22 divided by 6.02 exponential 23. Next, so I now have 0.02 moles, and don't forget that it's nitrogen gas. The key thing there is they're testing that you remember the fact that nitrogen travels around in pairs. So it's MR, nitrogen we know is 14.0, but it's in pairs, so 28.0 multiplied by 0.02. If you're wondering how I know to multiply it, number of moles is grams over rams. I want what's the mass. So I'm going to rearrange this, bring the rams over to there in order for me to get grams. So the relative molecular mass times by the number of moles will give me the mass. So times by 28, and I get an answer of 0.56 grams C. Let's move on. Next, when magnesium oxide reacts with dilute sulfuric acid, the equation is, what is the ionic equation? We talked about this last lesson. So we talked about the idea that all solids and liquids just remain the same, and gases too, by the way. The only one that you split into ions is the acid. So if we split this up, we know that the magnesium oxide is going to remain exactly the same because it's a solid. Any aqueous we split into its ions. 2H pluses plus SO42 minus goes to form its aqueous, so split it up, Mg2 plus SO42 minus goes and water. Right. Cancel out what cancels. The only two that vanish are those two. So there's my final answer. So the magnesium oxide is still there. So that eliminates, that gets rid of C and D. Yeah. But the sulfate ion should also now vanish. So A is wrong and B will be the correct answer. Let's just check that that is the right one. So these two on that side and those two on that side. Cool. There you go. So B is going to be the right answer. Let's move on. A solution of sodium chloride is prepared by dissolving 10 grams of a solid into distilled water and making the solution up to 250. I've suddenly realized, by the way, that if anybody wants to use this paper as opportunities to kind of check their own working, I would just say pause the video at each multiple choice I get to, have a go at it yourself, and then listen to my commentary. That sounds like a reasonable thing to do. In this case, it's given me grams, so number of moles is grams over rams. Yeah, we want moles, of course, because it's in the unit, and we want it per liter. So grams over rams will give me moles. We know that the grams is 10, and we know that sodium chloride is 23.0 plus 35.5, so 58.5. By the way, I actually know the MR of sodium chloride, but I mean, to be fair, in the exams, I always make sure I check anyway. I'm still just running it on my calculator with the numbers. So 10 divided by answer gives me 0.171 moles to 3 sig fig. Yep, but now I'm dissolving that. My next equation is number of moles is C times V over 1,000. If people are wondering where the 1,000 comes from, it comes from the fact that we're in centimeters cubed. So the 1,000 automatically converts it. I prefer this method than converting all volumes to DM. If you want to convert to DM first, knock yourself out and just use C times V. I totally get it. So I've got the moles. I know the volume, and I've got obviously the 1,000. So I'm going to rearrange this, multiply that by 1,000, and then divide it by volume. It'll give me C. Times 1,000, got the number still on my calculator, divide by a volume of 250, and I get a number of 0.684, which is B. Nice. It's nice just for me to show you that number. Times by 0.171 over a volume of 250, and I get my concentration as 0.684 moles per DM cubed. Oh, when GCSE. DM cubed. Love it. Moving on. Next. Okay. 10 test tubes, each containing 1 centimeter cubed of chromium chloride solution of concentration 0.1, placed into different volumes of silver nitrate solution of concentration. Oh, that's interesting. Same concentration. Yeah, that's interesting. Were added to the test tubes, giving a precipitate of silver chloride. That seems reasonable. The precipitate formed were allowed to settle, and the heights measured. Not a very good practical. It wouldn't work practically, but whatever. They never settle out the same. It's all a little bit wishy-washy, that practical, but still. I get the premise. So what we're doing is we've got volume of silver nitrate solution added in centimeters cubed. So we've added 1 centimeter cubed. We've actually added half. We've added halves as well. It's kind of nice to see that. But the precipitate has leveled off. It's nice for me just to draw the line. Has leveled off at 3. That means that at this point, we know that chromium chloride, they're going to ask us for the formula, aren't they? Yeah, okay. So just to explain what's going on, that the chromium chloride, by the way, which is actually chromium 3 chloride based on these numbers, I'll explain how I get to it. I can actually show you it with an X value here. So if I go chromium chloride X, yeah, so I don't know the number of them, that's going to dissociate to give me chromium. By the way, this we actually don't know its charge either. So plus question mark. But what we do know is we're going to get chloride ions. Yeah. Now, for those people who aren't sure what I'm doing here, if you do this, I'm dropping into teaching this a little bit further here, because this is actually a clever question. I like this question. So we've got, if we had chromium 1 chloride, I'd be forming these guys plus 1 Cl minus. If it was chromium 2 chloride, I'd be forming Cr2 plus 2 Cl minuses. If it's Cr3 plus, then I'm going to get chromium, looks like a G. I'm going to get chromium 3 plus 3 chloride ions. What we do know, though, is that silver nitrate is going to give us just one nitrate ion. It's going to give us Ag plus and Cl minus and NO3 minus. Yep. So based on this fact, if we're making a precipitate, it's because the silver ion is joining permanently to form the insoluble silver chloride as a solid. That we do know. If you don't know that chemical test, you should do by now. Oh, my laptop's just taking a break there for a minute. Oh, has it just? No way, has my laptop just crashed? No way. Give it a minute. It'll fix itself. Just takes a little time. Okay, there we go. So if you don't know this chemical test by now, you really should. So this is going to be the white precipitate of silver chloride. Now, what this means is that if we had one of those, and we have one of those and one of those, I would form one, let's just assume 1 centimeter cubed of the precipitate. But what we're realizing is I'm getting lots of I've got lots of those present, and then I'm adding in 1 centimeter of the silver nitrate, and it's reacting with each of these. And what that essentially means is the ratio of this is 3 to 1 of the chromium chloride. So that means it must be CrCl3 that's doing it, because it's giving me 3 Cl minuses. Each of those Cl minuses is going in here, and I'm going to need 3 times the quantity. I'm going to need 3 times the quantity of this in order to be able to pick up all of those chloride ions. So I know I've just multiplied the equation. Some students might not overly enjoy that explanation, but that's the premise that's happening here. It's giving us the ratio between the silver ions. So the ratio here is Ag plus is 3 compared to 1 chromium chloride, chromium ClX. And that's giving us just one of them. So what that means is in order to do that, that had to be 3. So my answer there is going to be D. Let's move on. Tricky question, that. Okay, the atomic number of the element scandium is 21, and the mass number of it, its only isotope is 45. What is the number of electrons in scandium 1+? Okay, that's quite clever. So, by the way, it's given us the element's number. It's element 21. You can find it on the table as 21. That means that in the original atom, scandium 21 and 45, yeah, we know that there would be 21 protons. We know that there'd be 21 electrons because they're always the same number in a neutral element. And the neutrons is going to be 45 minus 21. I never do it in my head. I know I can 24, but I'm going to do it anyway. Should never do anything in your head. It just opens you up. Sorry, I'll flip that over. 24 neutrons. But here's the thing. It's positive. So it's lost an electron. So the answer is it's going to have 20 electrons in order to make it positive. Yeah, so that there's an extra proton and electrons. 20 of them. Cool. Next. In the mass spectrum of scandium, form scandium 1+ and scandium 2+. What is the M/Z value for the mass spectrum peak of the scandium 2+? Okay, so if this is the only ion, we know that we've got mass over charge is what we call it, the M/Z value. Yeah, M/Z literally tells you what they're doing. It's the mass 45 over the charge. So if this is going to be a +2, I'm dividing 45 by 2. I know I can do it in my head, but I don't want to. 22.5 is going to be the peak I'm going to see. Cool. Nice and easy, that one, folks. Gotta love it. Which equation represents the first ionization energy of iodine? Okay, so in order to do this, the first thing to point out is symbols. So in order to ionize, you have to be a gas. So that eliminates A, and that I shouldn't do it like that. That eliminates A and C instantaneously. That's just a nice thing to remember, that the general equation is M gas. You're going to remove an electron to form M plus as a gas plus 1 electron. So this is what I'm looking for. Yeah, I need to form a single ion, but the thing is, the only thing that's complicated here is to recognize that the diatomic versus iodine, and that's interesting because the reason why B won't work is because I would have to have added in energy in order to split the iodine molecules apart. So that means my value for the ionization energy would be way too big because if I'm going to add loads more energy to the electrons. So the answer is going to be D. I've got a single atom forming a single ion, and it matches perfectly to my general equation for ionization energy number 1. Next, what is the electronic configuration of a the electron configuration of a nitrogen atom? Okay, so nitrogen atom is element number 7. Read the table. 1s2, back to the beginning, 2s2, 2s2, and then 2p3. So we can put into boxes. First thing is to recognize that B can't be the answer because that is not possible. When you fill up orbitals, they always enter in the same upward spin. They only flip to be a downward spin when somebody else is there. This is to minimize repulsion. Who's that? Pursuit of Studying. Hello. Thank you so much for coming. Pursuit, if you've got any questions about any of these, please just let me know in the chat and I'll happily talk you through it. So in this case, C and D are out the window. Yeah. The next one is A is incorrect because you can never have Hund's rule. You can never have 2 electrons in the same orbital with the same spin. So A is out the window too. My answer is C. Nice. Moving on. The element manganese has the atomic number 25. What are the numbers of sp.d electrons in an atom of manganese? Now that's really interesting. So manganese, we can do this all the way, folks, if we want to. 1s2, 2s2, just cross over the table, 2p6, back to the beginning, 3s2, skip over, 3p6. I haven't learned this, by the way, I'm just reading the table. Back to the beginning, 4s2. I ought to do this on a table, really. And manganese is 3d5. So 3d5. So the total numbers of s electrons is s's. Let's do the s's first. So we've got 2 plus 2 plus 2 plus 2. So 8 in total. There are my s's. So that now eliminates A and C. Next, these are my s's. My p's are next. Change my color. I know that you can't in your exam, but it's useful just for me to do it. 6 just to make a point. I'd lay this out in the same method, by the way, if I was doing it in an exam. Another 6 there, and I'm done. So that one's going to be 12. 12 p's, 8 s's. I'll actually put those next to it. I'll do a 12 p's there. Just kind of shows you what I'm doing. Yeah, so that now eliminates D from the question because there aren't 17 of them. And then the D electrons are going to be 5. There's my D's. So 5 for the D. I like it. So that's going to be B. Nice. Great question. I like that one. Never seen one of those before. It's neat. Total number of not going to make any difference. Okay. Which row in the table shows the correct forces in a lattice of lithium iodide? Okay, that's an interesting question. Lithium iodide is a molecular crystal. Oh no, oh blimey, that's really tricky. Oh guys, that's really odd. Lithium's and iodine, it's a ridiculously, oh wow. Okay, I might get this one wrong, folks. I'm just telling you my thoughts. Lithium is a very bizarre ion. Whenever I teach, I avoid lithium. Isn't it ionic? No, it's lithium iodide is not going to be because it's ridiculously tiny. Yeah, Pursuit, I totally get it. And it'd be interesting to see whether or not I might be overthinking this, but the iodide ion is massive. It's hugely distorted. It's a really good chance, and maybe it's just ionic with covalent character. Attractive forces between ions with opposite charges. Okay, well, every single one of those is true. So that's kind of neat. So, okay, they're telling me it's ionic. Repulsive forces between ions with like charges. You've got a tiny lithium, but it's a metal bonding with a non-metal. I know, Pursuit, it's okay. I totally get it. You've just got to be aware that A-level steps away from that, and it's now the difference in electronegativity. So it's just got a little bit more details going on here. This is a really tricky, some covalent bonding forces, yes. This is definitely covalent character. So the answer is, so A and B are now out the window because this is definitely going to be ionic with covalent character. Yeah, it has to be. Look how distorted the huge iodide ion is. This is going to be very quite a high percentage covalent character. Small cation, large anion leads to covalent character. We're probably going to get repulsive forces as well, because In a lattice structure, we've got we've got such a small cation and then enormous anions. They're massive. These are absolutely enormous. There's going to be repulsion between them. This is an A-star question, folks. This is a separator. I'm going to pick D, but most people here would pick C. I understand it. I might get it wrong. I might be overthinking it, but I'm going to say in a lithium iodide ion with iodide ions that are that large, these are going to repel each other because the lithium ion is so small, it's not going to be separating them by a huge amount. So that's a trick. That's a genuine A-star question. I'm picking D. I can't wait to mark that. If I was doing this as a practice, I'd want to mark that straight away to check that I'm getting it right. First one of real interest to me on an AS paper. Okay, some physical properties of 5 substances are shown. I know Pursuit's going to be sitting there going, how am I meant to know if there's going to be repulsion between the ions? I totally get it, Pursuit. It's an A-star question, this. What I would say is if you've got 2 very large ions that are the same charge in a lattice and a very small one, you get repulsion between ions as well. So it is a nightmare that. You need to look at some more questions of it. It's very important to do so. Some physical properties of 5 substances are shown. The letters are not element symbols. Okay. Which of these substances could be a metal? Okay, so let's just walk through all of them. So L has electrical conductivity as poor as a solid. So that's immediately not a metal. Yeah. As a liquid, it's good. So, and in solution. So this is going to be ionic straight off the bat. Next, M is good as a solid, good as a liquid, and reacts in water. So that's going to be a group 1. That's sodium, by the way. That's a metal. So this is, the clever thing is that they're looking to throw you off with the reaction with the water. So this is sodium metal. I recognize the melting point. So this is Na. This is a tick for the metal. So M definitely. Next, good conductor when solid, good conductor with liquid, insoluble in water. Look at the melting point. This is going to be silver or gold. So that is also a metal. 1083 could be copper. Copper, silver, and gold are all around about the same things, and I don't know the numbers off by heart, but I know that that's going to be one of those 3. But yes, this is definitely going to be a metal for sure. Tick. Next, poor in solid. No, that eliminates it, by the way, because we know one of the key properties of metals is they conduct electricity when solid. So the answer is going to be M and N. So M and N only. Going to go for C. Yeah, you can't have a metal with a poor conductivity. Which substance has properties showing that it changes from a molecular structure to an ionic when dissolved in water? Q. So the reason for this is because it's a poor conductor when solid. So this suggests covalent. It's a poor conductor when liquid. So it's not conducting when molten. This, again, is something like wax. Yeah. But then what's really interesting is it's a good conductor when dissolved in water. I can tell you exactly what that's going to be. It's going to be an acid. It's going to be something like citric acid. Citric acid is a really lovely substance because it low melting point, very easy to melt, doesn't conduct when solid or in molten, but it does when you dissolve it into water. Just to add to clarify some detail here, so the answer is Q. Just to clarify that, what's actually happening is the acids are special. This is a nota bene off this paper. Just to point out to you that acids conduct when dissolved, when aqueous. Dissolved and aqueous is the same thing, by the way. This is because we have the general formula of HX. And when it, as a solid, no ions. As a gas, no ions. But when it's dissolved in water, it forms H plus and X minus. And that now will conduct. Yeah, so just to explain what's going on there. It's dissociating to give me ions, and if ions are free to move, I'll conduct electricity. Next question. Nice question, though. At 180 degrees, aluminium chloride exists as Al2Cl6. By the way, this is called dimerization. So, dimerization. So, dimerization is when 2 molecules join together to form a single one. Yeah, it's called a dimer. Yeah, and in this case, it says, what is the structure of Al2Cl6? Well, 180 degrees Celsius, it forms a dimer. And the dimer looks like this. I need to be careful to get the direction of the arrows correct. And the answer is C. Now, some students will say, Mr. Duncan, why doesn't it exist as A? And the reason why it doesn't is because the melting point would be way higher than expected. Yeah, because it's becoming ionic, right? Melting point would be in the hundreds, 400, 500 to be ionic. Why does it not do this? The reason being is you can't form a standard covalent bond with aluminium. Aluminium has 3 electrons in its outer shell. So if I draw those 3 electrons there, it can form 3 standard covalent bonds to chlorine atoms, 3 standards like this. And aluminium does not have another electron to form a standard covalent bond. So that eliminates B out of the picture. Yeah, completely eliminates it. Because in order to do a standard covalent bond, it's a dot and a cross, right? Which means there'd have to be a cross or a dot there for it to be able to donate. But it doesn't have one, so A can't be true either. Now, the next thing is when it dimerizes, chlorine doesn't have an electron, a pair of electrons to give. This eliminates D. D's out the window because this dative covalent bond here is telling me that the electron pair in this bond is coming from the aluminium atom. But that can't be the case because we know that aluminium doesn't have any here, which means it must be getting its electrons from a chlorine atom on another molecule of AlCl3. So the chlorines, I'll draw it all out. This comes up quite regularly on pay. They like their AlCl3 dimer. They do like it. So what's happening here is that the pair of electrons on this chlorine is forming a dative covalent bond there, and this one's forming there. So they're then overlapping. So the answer is C. Neat question, like it. When carrying out chemical experiments, the hazards and risks must be considered. Agreed. For a given chemical, the hazard is fixed, but the risk varies. Yeah, that's correct. Hazard is what it could do to you. So, for example, fire, the hazard is its high temperature could lead to burns. That's the hazard, yeah? And you can't ever have cold fire, so the hazard will be fixed, yeah? But the risk will vary because we can alter the risk by having precautions. So I think A is correct, yeah? The hazard varies, but the risk is fixed? No, because risk is the probability, right? Both hazard and risk are fixed. Both hazard and risks vary. So I'm going to go for B because the hazards, I think, are fixed. You can't change a hazard. So hazards are fixed and risks vary. Yep, because we can change the risk by doing precautions. We can lower it. I'm going to go for A. That one, though, again, why not A? I've gone for A. The hazard is fixed, but the risk varies. I agree with this. If you're wondering why A not up here is because the melting point of that would be really high. That's a really odd thing for it to happen. Aluminium is in a really unstable situation here. It doesn't want to do this. Anyway, I don't know if you're talking about 12 or 13. I'm going for A. I'm in agreement with your pursuit. Nice. Heterolytic fission produces. Okay, so heterolytic fission, it's nice to do this in our picture. Heterolytic fission is when a bond splits to form 2 different charged ions. So in this case, I'm going to break it this way towards the Y, and I'm going to form, this will become positive, and Y will become negative. So they don't form free radicals. By the way, Y will also have a lone pair, and you should circle your charges. Cool. Free radicals only. No, incorrect. Ions only. That's not entirely true. Free radicals and positive ions only. Free radicals and negative ions only. Okay, so C and D are completely ridiculous because you can't ever get a free radical from heterolytic fission, so the only answer must be B. Nice. That was the fact that the other 2 are ridiculous that gives me that answer. Like it. Waiting for the page to load. Nice. A hydrocarbon X has a molar mass of 98. When a sample of X is shaken with bromine water, the color of the bromine water does not change. Which of these could be the structure of X? Okay, molecular mass 98, sample X shaken with bromine, the color of water does not change. So, okay, it does not change. So which one could be X? C. It's the only alkene because it says it doesn't change. Well, if it was C, then bromine water would have decolorized. Yeah, whereas this won't change bromine water, won't change bromine water, won't change bromine water. The question's throwing me off. A hydrocarbon X has a molar. When a sample of X is shaken with bromine water, the color of the bromine water does not change. Okay, right. So hang on a minute. Does not change. What could be X? It can't be C. Delete C. C is wrong. So hang on a minute. What's now interesting, we've got to count our carbons. Oh, good. It's the not. It always throws me off. Does it not change mean it remains orange? Yes, it remains orange, right? Correct, Pursuit. So 1, 2, 3, 4, 5, 6, 7. Okay, 7 carbons on A. And the other ones, so this is 7 carbons. 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons on him. And then 1, 2, 3, 4, 5, 6, 7. 7 carbons on him. Now we can add on the H's. Now we know that this is C7. I'm going to change that down to here. C7 and C8. These here are alkanes. So we just double it and add 2. H, 14, 16. This one's double it and add 2. 16, 18. Yeah. This one is cyclo, which means it's the same as an ene. So just double it. C7H, 14. So the question is, who's 78? Who's 98? Let's just check. So 12 times on calculator, 12 times 7 plus 16 gives me 100. A is out the window. Next. So, oh, that means it can't be B either. It must be D. So 12 times 7 plus 14 gives me 98. The answer is D. Nice. Cool. Yeah. Before it's not an alkene. Therefore it's not alkene. That's correct. Yeah, sorry. I hate those questions, Pursuit. It always breaks me. I don't like the not. It freaks my brain out. I'm dyslexic. That's why. Which of these atmospheric pollutants is not emitted during the combustion of a car? Yes, unburned fuel residue. The answer is A. You can't get ammonia. That would be madness. Yeah, so ammonia, nice and easy. The only way we make ammonia is through the Haber process, definitely not through burning fuels in cars. Just, by the way, if you're wondering where the nitrogen dioxide, nitrogen plus oxygen in the air at high temperatures at the spark plug, high temp, spark, I'm going to form NO2, balance the equation, half. Yeah, sulfur dioxide comes from sulfur impurities to form SO2. Both of these gases cause acid rain, and octane is called that's the one that other students might pick, but this is called unburnt fuel residue. This is, we don't burn all the fuel. Some of it escapes being unburnt, so it's spat out as a product. That's a clever question. Like that one. Hopefully everyone will pick ammonia though, because that's madness. Next. Sir, could you do a few unit 5s also? I will do. I'm doing paper ones over the next couple of days because the paper one is on Wednesday. I can't see anyone's name. It's really frustrating. I need to actually, you know what? I'm going to see if I can zoom in on my other screen. I'm just aware I can't see it. It doesn't matter. Yes, I will do some paper 5s and some paper 4s and 6s if I've got time. I will. Which of these occur in the propagation step of a reaction with methane? Okay, so number 1 is this is not a propagation, it's a termination. This one is a propagation, it is, and that one does occur. This is what you never see this particular step in the mechanism, by the way. This is a weird thing to do. Yeah, so technically those are correct. So B is a possibility. Just checking the others, why these might not happen. This one doesn't count because they're forming the same products. If I write these as equations, CH3 dot on the C, reacting with Cl2 to produce CH3Cl plus, that is indeed a propagation. Let's convert this one. This is CH3 dot on the C plus H plus CH plus CH4 goes to form CH3 dot on the C plus CH4. So that's not a propagation because it's the same equation, doesn't count. So this doesn't work. The next one is all a little bit weird. This one's super strange. There's no free radicals at all here, so D is complete garbage. So the answer is B. Next. What is the IUPAC name of the compound with the following structure? So don't be fooled, folks. Pause the video, have a go at doing it. Pursuit, I put C. That's okay. You're doing really well, Pursuit. I'm glad to have you here. It's a fun game to play, right? I might be wrong, Pursuit. Keep your answer. I might be wrong. So 1, 2, 3, 4 in a row. It's a trick, right? Oh, but they're all buttes anyway. So that's nice. It is a butte. Yeah. The next thing is we need to now figure out whether or not it's... it can be trans, by the way. It can be. I wouldn't do it like that, but still. So this is going to be, I've got, consider the carbon on the left. So this one has an atomic number of 6. This one's 1. This is low priority and high priority. Consider the carbon on the right. This is 17. This is 17 and this is 6. So this is high priority and this is low priority. So this is going to be an opposite side. Yeah, so it's going to be E. What's interesting is trans 2-chlorobutene. That's super weird. It is 2-chloro. So this is 2-chloro-butene, and it's going to be an E. Okay, so cis and trans, I always try to avoid cis and trans. This is going to be an interesting one, because considering you could possibly name this 2 of them. That's really interesting. You could do trans because there's an interesting thing, but the thing is the trans is then incorrect in terms of E and Z. So there's a contradiction here. So I'm going for my E because I think it's the better answer. I'm going for E there, but this one for me is an interesting one. 18 is going to flag up there as an interesting one for me. I'm going for C because it's an E, they're on opposite sides. It is better than cis and trans, but it might be trans. Because technically you could look at it like that, but I'd prefer E. Let's stick with that. Might get it wrong. Right, that's the end of the multiple choice. Now, I'm going to do something slightly different from my previous lesson. I'm going to mark the multiple choice straight away because there were a couple of questions I want answering. What is the difference between cis, trans, and E and Z? Right, so that's a great question, Pursuit. So just to do the quick lesson on this. So cis and trans is the old method and E and Z is the new one. And the reason why they do this, that there is a difference between the two. And I think I did this in my previous lesson. When you've got a double bond, they used to use cis and trans. Oh, that's my fire alarm for the school. So I'm going to have to stop my video here. Luckily, I finished the multiple choice. Before I run out, I have to, I'm afraid, folks. I'll come back to this, everybody, and I'll see you guys in a couple of minutes. I will end my video here.